Welcome back. This is Emmett, and in today's video we'll be tackling this problem. You can find the full collection of unique problems Mari and I created in the description. So, particle A's motion is defined by two parametric curves, x equals t and y equals e to the t, where t is seconds. Particle B is at the point 0.5, 6 when t equals 0. Particle B can travel at a maximum speed of 3 units per second. It does not have a specified path, but must travel in a straight line. So the question is, if particle B wants to intercept particle A in as little time as possible and can leave at the same time particle A leaves, t equals 0, what is the closest position to particle A's start that particle B can intercept particle A? Give the x and y coordinate of this position. So as always, pause the video, try it out, and get back to the video when you're ready. Okay, so that's a lot of info. The first thing I'm going to do is turn the parametric equations into y equals e to the x by eliminating the parameter. Since the first parametric equation is x equals t, we can substitute x in for t, and we get y equals e to the x. Now we can work in the xy plane with the point 0.5, 6. So let's start a little simple and pretend point B is stationary, and we just want to see the distance between it, 0.5, 6, and the curve y equals e to the x as time increases, where remember, x equals time. What we can do is make a distance formula between the fixed point and the variable point x, e to the x, where this point just represents any point along this curve. So let's let this fixed point be x2, y2, and this variable point be x1, y1. Okay, so now that we have that, we can use the distance formula to find an equation that will give us the distance between this curve and this point at any point along the curve. Drawing this out, we get something that looks like this, where the x values are also time, and the y values are the distances between the point 0.5, 6 and the curve y equals e to the x at a specified time. For example, if the time is here, the point would be here. But the problem is particle B can travel, period. It can travel. And it can travel at a maximum speed of 3 units per second. And it does not have a specified path, but it must travel in a straight line. So I'm going to draw out a new equation that represents the maximum distance that particle B can travel given a certain time. So for example, if the time were to be 2 seconds, the distance would be 6, since it can travel 3 units per second. And so if particle B wants to intercept particle A in as little time as possible, we need to find where this distance particle B can travel first equals the distance between the point and curve. And this happens to be right here. And so using either your graphing calculator or algebra, you can find that this point is 1.057, 3.171. And so to help visualize this solution, going back to the point and curve, if we draw 1.057, time equals 1.057, this is the first time that if the particle just starts traveling out in a straight direction, it can intercept the curve. Because before this, obviously at the very start, if it were to try and go back this way, it cannot travel at all. And then so as time increases, it can travel farther and farther until finally it reaches the curve. And so that's the answer. Although this was really wordy at the beginning, hopefully you saw how we could break down the problem into different parts and tackle it, just like Particle B tackled Particle A. As always, thanks for watching and have a good day.